Hi everyone, my name is Virali Soni and I am going to present a paper today titled The Verification of a Distributed System. Now we are going to discuss the overview, why is it necessary, solutions and the conclusion. So why is it necessary? Distributed systems are difficult to build and test because of two reasons: partial failure and asynchrony. Asynchrony is the non-determinism of a ordering and timing within a system. There is no now. Partial failure is the idea components can fail along the way, resulting in incomplete results. These two realities must be addressed in order to build correct distributed systems. Because of the complexity of the distributed systems and possibilities of failure, testing and verifying these systems are critically important. Now we have the solution called formal verification. Formal verification is a set of methods that prove properties about a system. Once these methods have been used, a system can say to be probably correct. There are so many methods like formal specification languages, model checking, monitoring, canary, unit and integration testing, and random checkers that we are going to discuss. Formal specification languages. Individual systems and protocols can be verified using formal methods such as TLA plus and COQ. These are formal specification languages that allow users to design, model, document, and verify the correctness of concurrent systems. Every system under test requires the definition of the program and environment, including what kind of failures can happen, and a correctness specification that defines the guarantees the system provides. With these tools, a system can be declared probably correct. Amazon Web Services successfully used TLA Plus to verify more than 10 core pieces of its infrastructure, including system simple storage service. Now the next solution is model checking. Another formal method, model checking, can also determine if a system is probably correct. Model checkers use state space exploration systematically to enumerate paths for a system. Once all paths have been executed, a system is said to be correct. Examples for model checkers include Spain, Amodest, TLC, and MacMC. Given the multitude of inputs and failure modes a system can experience. However, running an exhaustive model checker is incredibly time and resource consuming. Monitoring. Monitoring is often cited as a means for verifying and testing distributed systems. Monitoring includes metrics, logs, distributed tracing systems such as Dapper and Zipkin, and alerts. While monitoring the system and detecting errors is an important part of running any successful service and necessary for debugging failures, it is wholly reactive approach for validating distributed systems. Bugs can only found only Bugs can be found only once the code has made it into production and is affecting customers. All of these tools will provide visibility into what your system is currently doing versus what it has done in the past. Canarying. Canarying uses a deployment pattern in which new code is gradually introduced into production clusters. Instead of replacing all the nodes in the service with the new code, a few nodes are upgraded to the new version. The metrics or output from the canary nodes are compared with the nodes running the old version. If they are equivalent or better, more nodes can be upgraded to the canary version. If the canary nodes behave differently or are faulty, they are rolled back to the old version. If a canary test passes, the only guarantee you have is the canary version performs at least as well as the old version at this moment in time. Canary tests are most valuable for validating the new version works as expected in the common case, and no regression in this path have occurred in the service, but it is not sufficient for validating systems correctness. Unit and integration testing. Notably, the study shows that 3 or fewer nodes are sufficient to reproduce most failures. Testing error handling code could have prevented the majority of catastrophic failures. And incorrect error handling of non-fatal error is the cause of most catastrophic failures. Unit tests can use mockups to provide intra-system dependencies and verify the interactions of various components. In addition, integration tests can reuse the same test without the mockups to verify they run correctly in an actual environment. This testing can be done at low cost and it greatly improves the reliability of a distributed system. Random checkers. This is the last method. Libraries such as QuickCheck aim to provide property-based testing. QuickCheck allows users to specify properties about a program or a system. It then generates a configurable amount of random input and tests the system against that input. If the properties hold for all inputs, the system passes the test, otherwise a counterexample is written. While QuickCheck cannot declare a system probably correct, it helps increase confidence that the system is correct by exploring a large portion of its state space. Quick check is not designed explicitly for testing distributed system, but it can be used to generate input into distributed system, which can be used to discover and fix bugs in distributed database. Now conclusion. Formal methods can be used to verify a single component is probably correct, but composition of correct components does not necessarily yield a correct system. Additional verification is needed to prove the composition is correct. Verification in industry generally consists of unit test monitoring and canaries. While this provides some confidence in the system's correctness, it is not sufficient. More exhaustive unit and integration tests should be written. Tools such as random model checkers should be used to test a large subset of state space. Efficiently testing distributed system is not a solved problem, but combining these all methods, you can obtain higher confidence in system correctness. Thank you.